Good morning, everyone. On behalf of Velalar College of Engineering and Technology, I wish to extend a warm welcome to our guest of honor, Mr. R. Ilavendan, Data Scientist, PayPal, Chennai. I also welcome all the student participants. I wish to welcome our Head of Department, Dr. Mainavadi Ma'am, to take over. Thank you.
Hi, good morning, everyone. Good morning, Ilavendan.
Good morning, ma'am. How are you?
Yeah, I'm fine. And a pleasure to have you once again for our programming.
Thank you, ma'am. Yeah.
We shall start the session as you are waiting for more than 10 minutes, I hope so.
No, no, no problem, ma'am. We can start whenever everyone is ready. If everyone is ready, then we can start now.
Expecting our participants to join soon, and some were attending NPTEL exams, and only a few participants are here. Hope I could manage them with them.
Okay, ma'am. So, shall I start presenting and start this session?
Yeah, sure.
Yeah,
You can
sure.
take over the session.
Yeah. Thank you, ma'am. So, hello everyone. So, hopefully, you're seeing my screen now. Yes. So, yeah. So, this is the agenda for today. So, today we are going to see a small recap of what we have seen so far in the previous session, and then we are going to see a few more box plots, diagrams, and then the few more algorithms. And then post break, we are going to take a sample data set and then see how to approach a particular data science problem in general, because this particular part is I would say somewhat important, because so far what you have seen or what we are going to see in the first half of the session, if you connect all the dots, it is going to make much more sense when you start applying it in the real time. So that's the reason, so I wanted to show you a sample problem. So that is the agenda. And I will show you where we have left in the previous session. So here is the table of contents from the help document or help tutorial book that we have seen last time. So initially we have seen the evolution of R and how to set up the environment, and then to have the basic syntaxes, data types, etc. So the chapters 1 to 4 is basically saying basically nothing, just the environmental setups, and post that we had the or variables assignment and then operators decision making. So loops and function. So till chapter number 9, it is common again with the programming languages, the other programming languages that you guys maybe are familiar with, say C or C++ or Python, I guess. And then after chapter 9, we moved somewhat into strings and vectors and lists. So this is something unique to R. So unique as in you cannot see a vector in Python or in any other programming language. In strings, the handling of strings is very unique to R, and that is what we have seen. And the lists, matrices, and arrays are again, it is more or less on the common ground. So some features are available in the other programming languages and some are not. So that is where we have seen the basic introduction till chapter 14, and post which we have gone to the data frames, data reshaping, loading of the data, And after once we load the data, we have different types of files, say JSON file or CSV file or an XML file. Like most probably like 95 to 98% of the time you'll be given the data in a CSV file. So that is there. And we have also seen the databases in general, like basically how you do a SQL connection, SQL connection with your, the basic username and password. Like we have not seen in depth, but we have just seen that there is a feature available in our environment, and post which we have gone to the pie charts or the visualization aspects of R. I think this is where we have stopped. Like we started seeing the pie charts and the bar charts. So that is where we have stopped. So what we are going to do now is we are going to see the box plots, histograms, line graphs, and scatter plots. Like we are going to see in depth in all of these visualizations, because the bar charts and pie charts are something quite easy, but box plots, histograms, line graphs, and also we need to know certain things like how to interpret the data, so that so you always look into these visualizations before building a data science model. So these graphs are quite important, and post which we have this statistical variances, like statistical methods, say z-stat, t-stat, and other. So those are advanced metrics that are used for a variable to be measured. But then we'll just see the mean, median, and mode, and then we'll see a simple algorithms, say linear regression. And don't be scared by the names when you say linear regression, normal, and Poisson distribution and all. It is like, if we understand it, it is going to be a simple task. So we are going to see the linear, multiple, and logistic regressions. So the distributions, I'll just touch upon like what is required and what is what. But we are not going to do all those distributions or check the distribution, etc. In post which we'll just see the time series analysis. I think this will take up the enough time till the break. In post which what we'll do is we'll have a sample data set. So I have a data set, and then we'll start working on the data set. So this is the agenda for today. So let me jump right into the bar charts. So I think the bar chart is something that we have seen. So the box plot is where uh, where we need to be concentrating upon. So before going to the box plot, I'll explain it to you why these charts are important. So okay, so when we say variables, so in general there are two types of variables. So quantitative and qualitative. So the reason why I'm bringing up the quantitative and qualitative variable is it is important to know the difference between them in order to understand the upcoming charts. So that's the reason. That's the only reason. So the quantitative variable is quantitative. Yeah. So the quantitative variable is something that is measurable. Say, so in general terms, you can say that whatever is quantifiable, say weight or age or distance. So basically, anything numeric is a quantitative variable, because you're quantifying something and you're trying to achieve something with those particular numbers. So those are called the quantitative variables, and the qualitative variables are categorical variables. So in here we will have gender, country, and then what, category. So any sort of category. Say you're from this particular city, you're from your preference, and then your opinions. Everything will fall into this category. So basically, anything that is non-numeric, or so anything that can be put it into different buckets. Okay, so the reason why I brought up this topic just now is we are gonna have this box plot. So let me show you how a box plot is like, and then I'll I'll explain it to you guys, like why it is important to know the difference between the qualitative and the quantitative variable. So the reason being is, again, we are taking the same empty class data set that we have it in the last session. Yeah. So this is how typically a box plot works like. So the reason why I have shown the difference between the quantitative and the qualitative variable is, whenever you are given a variable, you should know which sort of chart that you want to use in your descriptive statistics. So say I'm giving you a data set of X, Y, Z, then you should know which charts to use for what sort of variables. So obviously, you cannot use the box plot for this categorical variables, such as gender, country, or category, because it does not. Even though if you provide any categories, it is not going to make much of sense if you want to look into the data. So most probably we'll be using the statistics, and then we'll be using the graphs only to describe the quantitative variables, because those are the ones you wanted to focus upon. Say if you are forecasting, or if you're categorizing, or uh, if you're doing any time series analysis, all you will be focusing on is the numerical variables. The qualitative variables, or something that you'll be doing it in later point in time, but not currently. So whenever you are given a data set, please keep in mind that there are just two divisions. One is numbers, and another one is categories. And numbers takes the top priority and not the categories. So this is the only this is the reason why we have these many charts and then statistical variables. Now, going on to the box plot. So what we have here is miles per gallon versus cylinder. So the number of cylinders is 4, 6, and 8, and the miles per gallon. So again, I think so. You must have a pretty good understanding of how this data set is being constructed. So what are we trying to show here is the distribution. So when I say distribution, what you can see here is, if you take the number of cylinders of 4, the distribution is very large. So when I say the distribution is very large, it is because you see the depth of the box. Like you see the depth, and then you see the width. So the depth is high, and then the width is also high. So I'll tell you what these notions are exactly. So whenever you have a data, uh, say you have a data from 1 to 10, you can always categorize those data into 4 quantiles. So I think so, guys. Today the session is going to be more of a technical session, like uh, somewhat more technical terms are going to be used. So I'll be going very slowly, and if anyone feels that it is faster, or if you don't comprehend or understand the things, then you can stop me so that we can discuss it the way you want to take ahead. Yeah, yeah. So the quantiles are nothing but the percentages. So when we say there is a difference between the percentage and the percentile. So similarly, quantiles are like 4 quantiles in the box plot. So one is Q1, Q2, Q3, and Q4. So I'll say you what each of those quantiles are in just a moment. Okay. So when I say 4 quantiles, this is what I mean. So the first quantile or first subset of data has 25% of the uh, distribution. In the second set of the quantile, including Q1 and Q2, it has like 50%. In the third quantile, it has 75%. In the fourth quantile, we have like 100%. So now, how you can interpret in the box plot is anything that is, so this particular line you see here, right? The bottom of the box. So anything below this particular line is 25 or 25th percentile or your Q1. So this dotted line and this line, so these all different interpretations. Like, you don't have to worry about it. You just give your whatever the number you have, along with whatever the base value that you want to see upon, and then the boxes will be generated. So what I was trying to say is anything below this particular line is your 25% of the data. Say we have the data from 1 to 10, then the 25% of data, say what is 25% of 10, 100, 1, 4, around 2 or 3, it will be in here. So, and this is the Q2 mark, meaning, so from here to here, I think it is Q1. So you see here, right? So the outside of the box, below the box, it is Q1, and above the box, till this mean line. So this is the average line. So from inside the box till here, it is Q2, which is 50th percentile. This one, and above the box, like from mean to the end of the box, it is 75th percentile, and from above the box to the another above top line is your 100% line. So basically your 10 will be present somewhere in here, your 5 will be present somewhere in here, and your 1 and 2 will be present somewhere in here. Okay. So this is important to understand the distribution of the variables. Why? Because we are seeing the we are seeing how the data is actually going to look like. So why I'm saying this is, when you make a chart, you can obviously make an inference. So when we have, say, 4-cylinder cars, you cannot say that this is going to be the miles per gallon for this is going to be the mileage for us, because the mileage varies from somewhere in 21 miles per gallon to somewhere, say, 35 or 36 miles per gallon. So it is, you cannot make any sort of inference. But if you go to the 6-cylinder cars, the distribution is very low. So with confidence, you can say that uh, on an average, if you have a 6-cylinder car, your miles per gallon or your mileage is going to be in this range, in 20 miles per gallon, or maybe there is a standard deviation applied to it. So it is plus or minus 1. 20 plus 1, which is 21, or 20 minus 1, which is 19. Mostly like 75% or 90% of the data is covered in this range. Again, it comes to the again, if you look at the data for 8-cylinder engine, so which is the third box plot. So if you see here, again, it's the same thing. So it is following the same inference as we have it in the previous class, meaning as soon as you start increasing your cylinders, number of cylinders, then your mileage is going to go down. But then with this 6-cylinder engine or 8-cylinder engine, no matter which car you have, you are expected to have a mileage of say 15 or uh, 20 miles, 20 miles per gallon. So this is how so interpret the data. Like the same thing cannot be made about the 4-cylinder engine, because you have so many cars in there, so many car makers and so many distributions. So you cannot make an observation. But with this sort of graph and with this sort of visualization, what you can do is you do not have to be deploying any data science model or anything. So with just like the common inference, or with just the basic business stats knowledge, you can make inference and you can present your data. So often the simple solutions work better, and this is one of the simple solutions. So I hope box plot is clear now, because box plot is used everywhere. So literally everywhere. So whenever you are trying to take any qualitative variable, like meaning the quantitative variable, you are supposed to see the distribution first, and then you are supposed to go to the designing the data science model, or you can just make an inference and say that, okay, so this is the A, B, and C are present. So I'm going to make an inference. So it is not going to exceed. So even if it is going to exceed, it is going to be minimal. So we're not going to be worrying about it. So this is how you interpret a box plot. So if you guys have any question, I'll just pause for a moment, and then we'll go ahead. Yes. Okay. We'll go ahead with the next topic. So this is again, so the box plot with the knots is something like you get it in your iPhones. Like instead of having a single box plot, it is just shaped like a dumbbell sort of thing, and then you don't. So these are just aesthetics. Like if you want to implement, it is well and good. Even if you don't implement, like no one is going to ask you any questions. Like putting on the color and then putting on the shape, etc., etc. So that is there. Now comes the histograms. Again, I'll just copy the code and then put it in here. This is again used to see the frequency. So if I see the histogram of the weight, how it is being distributed. So usually what happens is, whenever there is a histogram, we are going to see the frequency of that particular data, meaning so how frequent it is occurring and how frequent it is going to uh, how skewed your data is. So skewed as in, so sometimes you don't always get the data which is clean and simple and nice. So when I say skew, uh, let's assume that there is a data which has the numbers only numbers that are present are say 50. Then it is completely skewed. So we are not going to make any inference out of it. So similarly, if we have say 50, 50 or 100 numbers concentrated um, on that particular variable. For example, assume that we are doing a histogram for the date of birth in your class. Okay, so in your case, it will be somewhere around 2002 or 2003. Like probably. So what I'm trying to explain is making that variable or taking that particular quantitative variable does not make any sense. So when you put in the histogram, everything is going to be concentrated on only one data point. So that is the reason we have this. So we can also try it for the empty cars data set, I guess. Yep. So this is how your miles per gallon is distributed. Meaning, so if you see it in here, it is almost like a bell-shaped curve. So when I say bell-shaped curve, it okay. So I could not draw it in here, so I'm just going to show how a bell-shaped curve is going to. So this is how a bell-shaped curve is going to look like. So the reason why I showed you this curve is important because when you study any distributions or any statistical methods, it is obligated to to verify whether the distribution is normal or Poisson or skewed or something like that. So mostly you will be using the histograms. So that's the reason that I showed you this particular one. So uh, for miles per gallon, we have a pretty nice distribution. But if you look for the cylinders, it is not going to be, because in cylinders we just have like three variables, like three categories. So though we have a number, like for cylinders we have say 4 cylinders or 6 cylinders or 8 cylinders, you cannot use this particular variable for any of your so any of your inferences or any of the data science model as your target variable. So it will not make sense because the distribution is so high. We have 10 4-cylinder cars, 8 6-cylinder cars, and then 14 8-cylinder cars. So this is how it is going to be. So this is how you discard a variable saying that, okay, so this variable is not required for me. So I am going to discard this particular variable, and then I'll be using the other variables. Say the miles per gallon is a pretty variable because you have some nice distribution across the spectrum, say from 10 till 35. So we don't have to worry about it. If you want to build the data science model around it, probably you will go with the miles per gallon, not with the cylinders, because the cylinders does not serve as a good candidate for your use case. So both box plots and the histograms serve the same purpose. So that's the reason I have shown you both of these ones. We will go to the next one. So yeah, again, so the range of x and y values, it is something that we can decide upon. So if you want to have anything different, or if you want to have a color, you can do always whatever you want. But again, those are aesthetics part, like we do not have to worry much about the aesthetic part. Yes, now comes the line graphs. So line graphs are pretty important in the sense that when you go for the financial data over a given period of year, it is going to help you a lot, really a lot. So just a minute, I'll just copy the code and then I'll just paste it. Okay. Again, I'm just taking the simplest of the examples to show you how this particular data works, so that you guys don't get you guys can grasp the concept and not only the syntax of it. Okay, so now coming back to the line graphs. So why we are using the line graphs is because we want to see the financial data. So whenever something is represented over time, say be it a number of minutes so I'm saying number of minutes because sometimes you'll be asked to find out the anomalies in a production server. Say for example you have an Oracle server, and if someone is asking you to the predict the outages of that particular server, then what you will do is the very first thing you will do is plot the dots over a line. Say you have the data from 2019 or 20, then you take the data and then you see whether there are any outages in the regular intervals. Okay, then what you will do is, if you see the regular interval outages, say it is your Oracle server or any database server is going down for every week, then you can assume or you can interpret that, okay, so the server is going down, I need to do something about it, or the server is intentionally going down because your system administrator is working on it. Okay, so again, this is one of the important plots or important visualization tools, graphs, because it is used literally everywhere. So if we go for Amazon, they will know exactly when to forecast the demand and when to anticipate certain things. Say, okay, let's assume that for our argument's sake, right? So let's assume that fifth is your Diwali week. So Diwali just completed in India, like last week, I guess. Okay, so normally your sales, the Amazon sales goes somewhere like 10, 20, 30, and then less than 10 because it is not. It's there is no any season at all. But then when there comes a Diwali week, suddenly your sales started shooting up. The reason being that is a festival week and more people are expected to make more purchases. Obviously, you might have bought something, some even as small stuff. Say a paper or a pen or even your mobile cover. Anything you could have bought. But then the idea here is to ready the system for those sudden surge in the number of requests. So ideally, what uh, in PayPal or in any other e-commerce platform they do is they anticipate these things. For example, the coming Monday is like a Halloween week in everywhere else in the world, like most Western countries. So most people are expected to make purchases, and if your system goes down during these times, like again, so many factors come into the picture. Your brand name will get severely damaged, and your competitors will make fun of you, like in social media platforms, right? Like, say, XYZ is taking up the business of ABC, and if PayPal is going down, some of the competitors, say Square, they'll come into the picture and say that, hey, this competitor is not doing well, so please shift away from here. So the reason why I'm telling this as kind of a story is these line graphs are used to predict the seasonalities and the anomalies. So seasonality is nothing but you're anticipating a certain thing that you know for a fact that it will happen in this year and in this time frame. So when I say Diwali, this 1 week before and 2 days after Diwali. Like, so that is when most people spend time with their families, with their friends, etc. etc. So it is important to use this line graph or line plot during those times, and then make predictions and assumptions so that you get ready for what is already been there, because Diwali has been there for years and years, like 100, 200,000. It's been years, so we know for a fact that this anomaly or the sudden surge is going to happen. So we want ourselves to be prepared for that. So people will be so the more number of servers will be available for you, and then the more people will be available for you to help online in case of customer care, etc. Those sort of things. So in any company planning or any budget planning or any corporate finance, this line graph is like the bread and butter of the finance. So that's the reason I'm more emphasizing on this line graph so that you grasp the data idea. So yeah, again, this is a basic line graph. Like if you go through the details, say line, color, title, and charts and labels, whatnot, right? Like however you do it in Excel or in any other visualization tool, you're going to be there. So you can name the variables and name the X and Y axis, give a title chart. Even you can have a multiple line chart. Like it is all going to be there. But the basic idea is it will help you a lot if you're working in a corporate finance or in the financial sector, is the bottom line for this particular chart. Okay, so the scatter plots. So the scatter plots are another important ones. Why? Because it is used to establish a relationship between whatever you're predicted and the target variable. Okay. So now we are ready with the data. Yes. So the reason why scatter plot serves as a the basic starter for a data science model or any model is it tries to help us with establishing the relationships. Okay. So when I say relationships, we are targeting about the x and y variable. Like I'll say target variable is the variable that you want to predict. Predict as in uh, the variable that you're seeing to or that you're planning to give it to your final end user. So given variable will be your weight and the target variable will be your mileage. So why? Because is given the weight you can somewhat correlate to a mileage based on the scatter plot. So scatter plot is nothing but we are plotting on x and y, and instead of having like bars or pie charts or line charts, we are having a simple dot. It is a we are not connecting anything. We are just having the distribution. Okay, so if you see here, so let's assume this is your weight of the car or weight of let's assume this is the weight of the car. Okay, so as your so if you in general as a common notion, right, the cars which are smaller in lightweight, they provide you the more mileage, correct? So if you have own a car, or if you know someone who owns a car, or in general, again, if you're a car enthusiast, it is a given fact. But uh, it is a given fact for a common understanding. If someone asks you to, prove it through data, this is how you prove it. Because if you see it in here, as your weight increases, your mileage is start going down. So if you see here, say for the weight 2.5, we are having the mileage greater than 20 miles is what we are having. But as you grow through x, so as x grows through, if we go for 3.5, everything is below 20 miles per gallon, meaning so the weighter or the bulkier your car is, the less mileage you're supposed to get. So normally what you see is whenever you see a smaller car or say hatchbacks, the Maruti 800 Swifts and all, you'll see that the mileage is good. Why? Because they have smaller in size and they have less weight, etc., etc. But if you see a bigger cars, say Toyota, I mean Innova, and then other SUVs, they are taller. At the meantime, they have a more weight, and for the same reason, since they have to pull in more weight, their mileage is lower. But this is how you put it in a graph and say that, okay, so I have the data points, and based on my data points, I'm going to plot the variables and say that because of this particular reason, because as your weight increases, your mileage is decreasing. So this is how you interpret the data. Okay. Again, we have the matrices, like we can see multiple variables, we can compare the multiple variables, but just for the moment, just keep in mind that the scatter plot is about all about the distributions, and you know it is going to help us in selecting the variable and finding the relationship. So so when I say the relationship, we just now we have established that we have a inverse linear relationship, meaning, so if I draw a line from here to here, so I'm sorry I could not draw it in here, so that's the reason I'm using the cursor in here. So if I draw a line from here to here, like this, then what we can say is, as your as your weight starts to increase, your mileage starts to decrease. So that's how you can establish a relationship between two of your variables. Okay. Okay. So I think we are done with the visualization part. So now we can move to say the statistical notions, say the mean, median, and the mode. We quickly go through the time. Yeah, we still have time. So yeah, so mean is nothing but your average. Average as in, like, so you have a set of, say, uh, 10, 20 and 10, 20, then your average will be something around 15 or something. So that is the average. And median is nothing but whatever the data point present in the midpoint of the data is your median, and the mode is frequently occurring data point. So it is again the mean, median, and mode are like the basic statistical things. There are so many other variables. However, I have shown you this mean, median, and mode because it is good to know the statistical inferences of your variables. Okay. So again, the syntax is going to be exactly the simple way. So when I say mean, you just put a mean of, okay, I'll just type it in here. Mean of, what is the variable? Okay, miles per gallon. You see this? Like, so on an average, the miles per gallon, or the mileage that is given by any car, is 20 miles per gallon. So we can easily say that, because if we see here, most of them around above this line, above this 20 line, has like data points are above, and some data points are below. But if we are asked to do that by calculating in our mind, it will be tedious or difficult for us. So that's the reason these functions are present. So okay, we'll do the mean, and then okay. Okay, so okay, so let us. So in here, I wanted to explain you the two things, but that one we will do it later. But just for now, you can just keep in mind that in mean you can exclude certain sort of variables. For example, if you look at the empty cars data set, everything is nice and clean. So in a real world scenario, this is not the case, because often you have some outlier data, or often you do not have data at all. So meaning, so for example, uh, if we do not have the miles per gallon because of some technical glitch or some issue in the data collection, then the function might not be working as it is as it is working now. So in that case, what you'll do is, by default, the na.rm feature. So it's nothing but na is not available and rm is removed. So if by default this is set to false, but if you have any discrepancy or any issues in the data, then you'll remove this false option to true option, and then you will calculate the mean for the entire data set. So for the just keep in mind that it is just one of the methods to remove the outliers or the remove the null values. So removing the null values might be the best term to coin in, because that way you can easily correlate. So we'll check for the median. So median is again 19.2. So in the mode, which is the most occurring one. Okay. Yeah. Okay. So for mode, we do not have a inbuilt function, so we have to write a function like this. So we'll just copy this one and then yeah. Since I copy pasted it, there was some issue in the copy pasting, so that's the reason this get mode function is throwing some the symbol error. So if I type it in here, ideally it should work. Let us see. Sometimes this is an issue with R, like when you uh, when you try to copy paste things from certain documents because of regulatory issues and I don't know, some issues, like the R environment does not recognize your command. Basically, if you see, the 54 line and the 56 line is one and the same. It is just that because of the copy paste, there is some characters in between that is preventing you from performing certain operations. So again, this is nothing but a formatting issue. But then if you type in the code exactly, like I'm lazy to type in the code, so that's the reason I copy pasted it from there. So that's the reason it didn't work the way it is supposed to work. Okay, so now we'll get the mode for. Yep. So the most number of occurrences for the miles per gallon or mileage is say 21. Again, it's a known fact because from our scatter plot we have already seen it. So if you see here, in 21 we have say 1, 1, 2, and 3. I guess that's the most occurring thing in a single given line. So others are like either above or below. So it is known for us from the graph, but then if you want to do it uh, in the numerical value or represent it, then this is the good way. So we have seen this. Yes. Now coming to the linear regression part. Like here is where the real data science work begins. So far, if you have any questions, any comments in the chat box or anything. Cool. So we'll move ahead and then we'll see some of the algorithms and then we'll take a break around say 10:40 and then we'll be back at say 10:55 or 11, probably 10:55, and then we'll have like the next session dedicated for uh, for having a sample data set and how to apply these models in the particular data set. Okay, so we'll go to the page one and just see how the algorithms are. Okay, you see here, right? So okay, the linear regression, multiple regression, and the logistic regression. So in the start of the class, we discussed about the two variables. One is quantitative and another one is qualitative. So quantitative is for numerical variables and qualitative is for, the categorical variables. So again, for quantitative, we will go ahead with the linear regression, and for qualitative, we will go ahead with the logistic regression because we want to categorize the data. So uh, the idea behind both these regression methods is to find out the value given the data in some specific format. Say, if you want to predict or forecast the weight or age, or even if you want to forecast a sales in the Amazon working example that we have seen, then it is then we need to have certain sort of measures just to have these data science models work. So I do not want to go into say in detail about the statistical part of it because these equations are somewhat tedious, but if you understand it, it is going to be the easier one. I'm just copy pasting the data. Okay. Okay, so before jumping onto this, let us have a common understanding, right? So what happens is, let's say you want to predict a variable age. What is the thing that comes into your mind while predicting your age? For example, if you go into a street, if you step outside and then see a person A, and then you want to guess his age, then what are the parameters that comes into your mind? Like obviously his looks, his skin tone, his hair, and then maybe his height, or there are so many parameters around it. But what are the parameters that in our personal opinion that affects his age? Obviously only the skin tone, and then and then the and then their eyes probably, and then the hair. Okay, but can you predict a person's age only with their height? I do not think so, because there are people of uh, different height in every age. Okay, so this is sort of a correlation that we already do it in our mind without knowing that we are doing a relationship to arrive at a variable. For example, if I ask a person to guess my age, then you'll say probably based on my looks, my skin tone, and my color, my hair, you'll say somewhere between 27 to 29. That will be a good estimate. Obviously, if you see an older person, then their skin will be somewhat shrinked, and they'll be struggling to walk, and most people have their hair gray hair or white hair, and then you'll say that their age must be above 50 or 60. Okay, but you'll not come to the conclusion that a person is, so I'm say 5'7" or 5'8", then you'll not say that because you're 5'8", your age is some X and Y. You'll not say that. Okay, so this is how you typically guess your age in when I ask you to guess anyone's age. So why I'm giving you this example is there is a relationship between the variables. So when I'm asking you to guess the age, there is a relationship between the skin, the hair, and the age. But between the height and the age, there is no relationship, because you can never say that. I'm keep on saying this again and again, because to get you some introduction about the idea, because we are going to see the relationship part over and over for like say next 1 or 1.5 hours. Okay, so I hope you guys are clear with the relationship part and what affects your final age variable and what does not affect your final variable. So do you guys have any question? I'll take a moment in here. I don't see any questions. Will I think that's a pretty simple example. I guess so. Obviously, everyone should be okay. Yep. So don't be scared of these things. It is not like something you study in your digital signal processing and all. So it's like a simple math. Okay. So what we are trying to do is you have an X variable and you have a Y variable, and uh, LM is for a linear regression model. So this is used to fit your linear models and used to find the relationship between the two variables X and Y. Okay, so whenever there is X and Y, so obviously in your math classes, or I don't know, in M3 or M2, I guess so, you must have seen this equation of slope. Y is equal to mx plus b or c or a. So what does that mean? Meaning, so let me go back to the equation. So y is equal to ax plus b. Okay, so y is your response variable or your target variable. So whatever you want to achieve it. Okay, x is your predictor variable, which is, so x is more or less, I'll write it in here so that you guys don't get confused. So this is a simple slope equation, I guess. So it is the same for all the linear regression models. Okay, so where y is equal to what? Y is equal to the resultant variable. And x is equal to what? Your predictor variable. So for generic example, for us, y is the age, because y is what you're trying to guess from a person's looks. Okay, and x is your predictor variable. So when I say predictor variable, say skin tone, hair color, etc., etc. So you're trying to form some relationship between these two, and then you give your age estimate based on this one. Okay, so don't worry about don't think too much about it, because it's just again a simple example that I'm pulling out of my head. Like, it's nothing complex. And then you're saying that y is equal to mx plus b. So don't go for like mathematical notations for now, because in R or in any data science software, you're not supposed to concentrate on or do some math for anything. So everything is inbuilt function, so you don't have to worry about it. But there is the relationship is established by this particular m and this particular some coefficient. Okay, so why I say m is, so I'll tell you the reasoning behind. So m is nothing but your slope. So you remember whatever we have it, whatever we have in here, like we have established a relationship sort of thing. So that is your linear relationship. So what you'll do is you'll draw a line from here to here, and then you draw a slope. I hope you guys are I hope I believe that you guys are aware of slope, because you'll be so you'll be studying it from, say, what from your 12th standard or 10th standard. So slope is nothing but a raise over a range. Like you draw a line or triangle in here, and then you draw the slope, and then you substitute that numerical value in here, and b is nothing but your coefficient, say some error value of sort. So this is your typical real world example of your slope. So probably in your math class or any sort of maths class, like you could have asked yourself, like, why am I what am I supposed to do with this slope, which is and where it is being used. So in this particular equation, it is used because we have seen for a fact that as your weight increases, your mileage decreases. So that is your rise over range. So whatever the formula that you have for slope, say in your math classes, it is like y1 minus x1, I don't know, y1 minus y2 by x1 minus x2. So some sort of anything. But the general slope idea is this: you establish a relationship between two variables, you find out a numerical variable, and you apply it with your x value to predict your y value. So this is the simple concept behind this, the linear regression or linear modeling. So whenever someone says linear modeling from now on, like, you can always associate with a slope, or slope is your the benchmark. So wherever you have the linear relationship, you can take a slope and then say that okay, so with some level of confidence, I can say that this is going to give me some exact estimates. Okay, so I hope this is clear for you guys. So if you want to have any questions or any comments, we can take it for now, because the slope concept and the equation is. I said I'll not explain the equation, but then I explained it because I wanted to make the concept clear. So that is the only reason, nothing more, nothing less. So I hope you guys are clear. So I okay. Uh, do you mind typing your question, or you want to, like? Okay, so are you clear with the uh, concepts, Karunambika? Cool. Yeah, thank you. So yeah, we'll just move ahead for the next uh, for the next part of, like, a linear regression. So far what we have done, we have we have just established the relationship, and we have just understood the equation, whatever the a complex equation it is, like y is equal to mx plus b or c. It is simple equation that we have seen so far. But how would you use it in the functions, and how would you get your the final coefficient, whatever the b is? We have written it, right? So for writing the b, or for finding out the b, we do not have to do anything. Like, again, it comes from the fact that we can design our you know we can design our models, and then we can find out the relationship, and then we can predict the y variable. Okay, I'm going to copy the entire thing, because it will take some more time to type in and then see. Oh, this already there. So okay. So this one we have seen the same data. Yes. You see this one, right? Like don't worry about anything. Like say it has multiple variables or coefficients, etc., etc. Like don't worry about anything. Uh, just concentrate on the intercepts. So this one, right? So this is the intercept that uh, that you want to concentrate on. So again, I'll just give you a basic introduction about what is an intercept is. Okay, so intercept is a point where your line crosses your the x or y axis. So if it is an x intercept, so let's assume this is x axis and this is y axis, and let's assume some line is going in here, then the intercept will be somewhere in 4.2, and if it's a y intercept, then the line goes from here to here, and your y intercept comes around say 24 24. Again, it's a guess, but then the idea here is it's an intercept. Okay, so again, coming back to the equation. So now we have almost all the parts. So we have x, we have y, and we have this b. Like b is nothing but whatever the coefficient or the intercept or something, anything that you want to have. Like, okay, so let's assume you have some certain x value, say 151. Okay, for example, so this is again a sample calculation, not the actual calculation that is happening inside your the modeling. Okay, so this is 151, and for slope, for our calculation purposes, I'm just taking 10. It's not like actual slope, but it's just for the the representative value. And plus x is what missing for us. So but when you give the summary of the relations, then you have the coefficients, like the x intercept as negative 38. So negative 38 is, so x is negative 38. So what you'll do is 15 into 10 minus 38. So 1510 minus 38. So this is your the final y predicted value. So again, it is represented. It's just a sample, not representative of the algorithm that is actually going in there. Okay. Okay. So you have successfully completed your first linear regression problem. So all you are doing is you're taking an x and you're having a y variable, and then you're trying to see the relationship between the x and the y. So again, it is simple. You just type in lm and then say y tilde symbol x, and then you get the coefficient or the relationship between the x and the y, and you also get the slope value, and then uh, you calculate it, like the x coefficient, or the mx value is say zero point 0.6, and it is negative 38. So if we have to do the real calculation for 151 into zero point 0.6 minus 38, yeah, yep, 52.6 is your final predicted y value. So if you see this 52, it is more or less in line with the y value. So if you order the y variable in a ascending order, it starts from 47, 56, 57, so on and so forth, 62, 63, and the 52.6 is nothing but your the final predicted y value. Okay, so this is how you model a particular data science model. Say in here it is x and y, so that's why it's simple. But if you want to quantify something, say if you want to quantify your I don't know, your the subject between, I mean, your score in two different subjects, you can do so. Meaning, so let's assume you have a probability queuing theory, and you want to correlate with your scores or your grades in your marks in some other M3, then you can do X and Y, and then you just give this line, and then you calculate, and then you have this, say the X coefficient and the intercept value, and then you just start predicting your M4 score based on your M3 score. So that's how it is going to be. Like initially, it is going to be simpler problems like this, but then as you move on and on, you will be focusing more on the other statistical notions. So for now, I'm asking you, don't concentrate anything on this significant codes or residual standard errors. No, nothing. No, you don't worry about anything. You just worry about only the two parameters. So one is your x coefficient, which is your slope value, which is zero point 0.6, and your intercept value, whatever the negative 38 or plus 20, 200, anything that you're getting. So you're clear, right? So how the formula works in here, or how the equation is working in the back end. Okay, so that if you give any sort of variable, you finally get a final y variable, and it is obviously in line with whatever we have given as an input data. So I hope you guys are clear. Again, I'm taking a pause. So 10:40, will take, say, 10 minutes or 15 minutes break probably, and then we group together to work on a problem. I thought I will cover on the other logistic regressions and all, but don't worry. Like if you understand this concept, more or less everything is going to be the similar thing. Only one is like, instead of LM, you will be doing GLM or OLM, like depending on the algorithms. Like that one, you can learn it on your own. So for now, we'll take a break of, say, 10 minutes or 15 minutes. So we'll start at 10 for 10:50 to 10:55. So we'll start somewhere between the time, and then we'll work on a real world problem. Yeah, real world problem, and then we'll conclude the session then. We'll take a short break and then come back. I think so. Most of the people would be available by now, and I hope we can start the session, like the second half of the session. So wherein we will be taking the data set and we will be doing some sort of inferences around this particular um, data set. Okay. So again, so to start with, this data set is going to be the guide for you to scroll through or to know everything about the uh, data science and other things. But uh, this will help you understand each and everything. So whatever the algorithms we did not cover in this particular document, right? Like the logistic regression and the other ones, right? So I'll just, yeah. So again, to make a summary, so we have seen the linear regression and the multiple regression in the logistic in this distributions and all, like we haven't seen. And most importantly, decision trees are also not something that we have not covered in the previous session, because all of these algorithms, one way or other, it will be covered in the upcoming session, like upcoming session as in this session. And these random forest tests and all, like we will see, like don't be surprised by the random technical jargons. So what I would suggest is, like, just if you enjoy the process, you'll learn at least something from the session, is what I'm assuming. So yeah, let me start with the data set, with explaining the data set first. Okay. So I think most of us, like I believe that 95% of us have seen the movie Titanic, right? So I think it is fair to assume, because it is a cultural thing. Like whoever is obsessed with the Hollywood movies, they start with the Titanic, and then I don't know, maybe Avatar, and then start from there. Okay, so now we are going to case study the Titanic ship. Okay, we all know that the Titanic ship has met with an accident, and some people survived, and some people did not survive, and I don't know. Some people are rich, some people are poor. If you know the screenplay and story, we know everything, right? Like I assume that, because it is known, it's a known fact. Okay, but now we have a publicly available data set for the Titanic, for all the passengers who survived, who did not survive. What is the ticket range? I mean, what is the ticket number? And then what is their class? What is their age? What is their sex, gender? How many? Okay, I'll just explain the columns currently. So this is just a passenger ID. It's nothing but, so I just have like only 57 for in the it displayed in here, like, but we have like the entire list of, like, say 1800 or something. So it goes on and on, is what I'm trying to say. Basically we have like a complete list. So okay, so to start with, we have the passenger ID. So the passenger ID is nothing but your primary key if you associate with your database management systems. It's simply an indicator, nothing more, nothing less. Yeah. And then survived. So this is again a categorical variable, because so though it shows number, though it shows 0 and 1, it is it's nothing. It just says that they have some. Yeah. So okay, it's just nothing but, like, so uh, it just says whether they have survived or not. So meaning, so in the accident, if they have survived, then it is yes. Then if they did not survive, then it is no. So it is not like we do not have uh, uh, it's not like this is a quantitative variable. It is like it's like a qualitative variable where we have clearly we have the categories by seeing at by looking at the numbers we can see, but again we will establish during our process. Again, same comes to the passenger class as in like the first class or second class or third class. So these are the scenarios where we need to apply our knowledge and say that though the numbers are present, we can say that this is a categorical variable, not the numerical variable, though the numbers are present. Like we can easily map 1, 2, 3 to the first class, second class, and third class, just like how we have it in the trains. Again, we can easily map this 1 and 0 to survived and unsurvived, but the data will still look the same. But if you look at the fare, we cannot do so. We cannot do the particular mapping for the fares. So again, so it's just connecting the dots between all the learnings that we have so far currently. So that's the reason. Okay, so name is nothing but the passenger name, and here is the gender, their age. Uh, this is nothing but siblings and spouses. So siblings, like if we come with a family, like if I come with my sister or brother, or if I come with my wife, or if in case of a lady she comes with a wife, a husband, or her relatives, that sort of thing. Like it just says how many siblings and spouses we have. Like we have 1, 3, 4. Mostly we have 0. So it's just again a numerical variable. Okay. Again, what? Yeah. So this part is like parents and children. Like whether they have parents or and children on board on Titanic. Like uh, on board as in say whether they have boarded Titanic or not. Like the parents and children might be living elsewhere, but for our use case, like we are just taking the passengers who traveled on that particular day. Okay, so ticket number is again something. I don't think so. It will be useful for us. Like name, we do not have any particular significance for this ticket number, but the fare we can say the fare is somewhat significant, and then the cabin is like the cabin in which they traveled, and they embarked on which class. So embark as in they, whenever you board a ship or a plane, uh, you embark on a class. If you're a business class, you have a priority boarding or priority check-in. If you're a economy or economy class, you'll not have that. You have a premium economy or a business class. Say it's another way of differentiating the rich and the poor. So just let's just keep it that way. Okay, so now our idea is to so to find out any a relationship between the variables and their survival rate. Meaning, so to put it in blunt terms, if you are rich, are you supposed to survive? And if you have money, whether does it have any impact on being survived in the particular incident or not? Because we have a whole list of data. Like we have passengers from everywhere. Like I don't know how many passengers exactly traveled in there. I think it must be around some 2000. So 2000 is a good number to start with for any data. So what we are trying to see is trying to model is we are trying to see whether they have survived or not based on whatever the class or whatever the gender, the sex ratio, the age, the siblings and spouse, the parents and children, etc., etc. And we'll go one variable by one, and then we'll see whether there is a relationship, whether there is a strong relationship, or whether there is a weak relationship or no relationship at all. And then we're gonna say that based on this variable, he is likely to survive some X percentage because he is boarding in the first class with some, I don't know, some cabin and embarked on this journey. Like, so that's the general idea behind this exercise. Okay, I hope I have made the data set clear. So we will move ahead to the coding part. Okay. So for this particular exercise, I have already created the code, so we do not have to type in anything, so that I will be just focusing on the methodology. Okay. So the train data set is what like will be using. So basically, right. So let me start from where I have got this train and test data set. So if you go into a Google or any other search engine, Titanic dataset download, you have like n number of data. So uh, I'm pretty sure that almost all the websites will have the Titanic dataset, but for our integrity, like I usually take it from the GitHub, because that is where like most developers put in their code and collaborate and do certain things. Yeah, it's the same. So the passenger ID survived, passenger class, name, sex, age, and then siblings and spouse, parents, children, and the ticket number. So it is going to be the same. And whatever we have, like say around 892 passengers, and then we have the same data. Like you can find it anywhere in any website. If you want to download, like you can download this, but the data is same. Just for our the verification purposes, we are gonna see whether the ticket number is A5 to 1171. So it is the same. Like that's what I'm trying to say. Like for your training purposes, if you take the data from somewhere, um, make sure that the data is authentic. The data comes from a particular authentic source, and the data is so usable. Okay. So in our case, in the Titanic data set, it is same everywhere. So that's the reason I'm taking that data from the internet and using it for our the education purposes. Now back to the environment. Yep. So we have taken the data. So I have named that data as train data. So train data as in we are gonna train our model in this data, and then we are gonna evaluate the different models on the test data. So we have some 892 passengers, and we are gonna evaluate our models based on those, based on their actual survival rate. Why? Because we already have the results in here, meaning so we already know already know whether they have survived or not. Okay. So what we are trying to do is we will eliminate this column from the train data set. We will have the other variables, say passenger class, passenger gender, passenger age, sibling and spouse count, parents and children count, and these will be the X variables, meaning so these are the predictor variables, and your survived will be your Y variable or the resultant variable, right? Like I hope I have made the things clear. So if you have taken the linear regression model, you have taken Y is equal to mx plus b, which is in here. So Y is equal to mx plus b, and Y is the resultant variable, and X is the predictor variable. Again, the same equation is going to be present in here. So Y is your survived or not. So that variable, that result we already have, but we are trying to see whether there are any predictor variables, say gender, and then the passenger class, and then what? Siblings and spouse, and then parents and children, etc. So we have so many variables. So this is not you might have a question saying like why are we trying to design a model if we already have the survived data. Okay. So this is not a real world example. Again, this is an this is for like our understanding purposes. Okay. So in real world, how it works is, or how it works in PayPal is, what we do is we take the data till the end of the last month. So let's say this is 29th October. We take the data till September 30, and then we'll try to design or fine tune our models by adjusting the parameters here and there to arrive at a y variable. So by the end of the October, we'll have the financials coming in, and we'll compare our already forecasted variables with the October actual data that comes in. Okay, so when you compare the forecasted data and the actual data by the end of the October, then we'll say to the stakeholders, the internal finance folks, saying that our financial forecast model or whatever the model it is performing as expected. We do not have to do anything. If there is an anomaly, or if they want us to change anything, then we'll code something, and then we'll fine tune it, adjust the parameters here and there, and then we'll adjust the models to match more with the actuals, uh, and then it goes on. It's a continuous process. So when you want to become a data scientist, like, or work in a data science field in particular, you should know that it is always a continuous process. Like, no single model gives you the exact result in a given day, and it is subject to change as more real time data comes in. You are supposed to change or adapt your models. So you're not going to do any random modeling stuff. Like, we will get to know the models and how we work on, etc, etc. Okay, so we will go into the data set. Okay, so this Psych and Amelia are two libraries, that I'm going to use for the visualization purposes. Like, we have n number of visualization packages, but I'm going to use these ones because I usually prefer them. Okay. Okay. First things first. So, who's missing and who's not missing? Okay. So if you see here, okay, we'll just view the data frame first. So this is the data frame. This is the data that we read it from the um, or from what? From the Excel file or the CSV file that we downloaded. Okay. So what it does is, uh, it just gives you the missingness map. You remember we tried to evaluate or calculate the mean as in the average. So in our empty cost data set, so which is right around here, there is no missing data. So remember, if you remember that time, I told you that this is not representative of real time data, because in real time it is not always that you'll get a nice and clean data. Okay, so that's the reason we are doing this missingness map across all the variables that we have. So we just give the missingness map. Okay, so again, I'll be going in a faster manner. If you want me to stop somewhere, you can just stop me and ask questions. But regarding the syntaxes and all, like, for the missingness map and other UI tools, like, other UI commands, like, I'll share the code with your professor and ma'am, and then so that you can go through the codes. Like, we will not be going through in detail about the syntax, so we'll be focusing only on the business problems. This is just to set some context. Okay, because otherwise you'll be worried, because this is not something that is pretty new to you. So that's the reason I'm telling you. Okay, back to reading the map. Okay, so what it says is, in cabin and age, like, we have some missing values. So particularly in cabin details, we have the dark circles, or dark lines, meaning, so most of these values are missing. We do not have the real time data. So you see here, so we do not have a cabin data. Like, for every 10 or so passengers, we have three cabin details. So again, as a common sense, we will not be going with the cabin details, because we should be ignoring this particular column altogether. Okay, because we do not have the data, first of all, and the missing data is too high. It's like say 30% of only 30% of the data is available and not more than that. But if you look for the other variables, okay, if you look for the other variables, say embark has like one thin line in here and one thin line in here. So that is okay, bearable. Like you have some 892 samples and two samples are missing. You can still, adapt it to use it in your data. So that is okay. Even better, we have no missing values in all the other variables like fare, ticket, parents and children, siblings and spouse, and then your gender, etc. etc. Like we have the entire data. There is no missing value in here. Like we can observe the value. So that's what your missingness map gives. It just says that uh, 8% of the total data is missing in the cabin details. So we are going to ignore this cabin even before we start modeling or even before we start doing anything. So that's the idea behind this missingness map. Okay. Okay. So now that we know that, we are going to exclude that cabin in here. So if you see here, excluding cabin variable, I'll just call it as excluding cabin variable, because in here we have the library, and then if you see we have selected everything: survived, passenger class, age, gender, and then siblings and spouse, etc. etc. But we do not have the cabin because that is no longer needed for us. Even if you have it, like you have only 30% of the data, and we are not going to derive any useful information from that particular variable. Okay. Now, coming to the missing value treatment. So let's assume we first eliminated the entire cabin variable. Okay. Now coming to the missing value treatment. Missing value treatment as in, for example, here the ones for Williams, Charles, Eugene, right? So okay, that is not a perfect example, but I'll try to show you some example. Okay. Huh. We'll take this particular guy, Vulner Hugh, right? So for him, we have the cabin level details, but we do not have the age, right? So you see this column, age, column number G. I'm just try to highlight this. So hopefully it is visible for all of us. Okay, I'm just singling out that column. So if you see here, he has the cabin level details, but he does not have the age value. So what are we going to do with the missing value for age? Can we predict the age based on whatever the information? He's from first class, male. But what is the statistical significance of Mr. Hugh Wilner? It's literally nothing, right? So what we are going to do is we are going to take the guy out from our samples. Okay, so that's what we are doing here. Na dot omit. So na dot omit, what it does is in any given column, if there is no value, then we are going to omit that guy altogether. Remember, if you have given this na dot omit before excluding the cabin details, we are going to end up only with some 30% of the data. 30% of 900 is what? Some 200 to 220 people, which is not even bare minimum, right? So that's the reason you have to do everything in a step by step manner. Like see which is where the missing values are concentrated, exclude that column first, exclude this cabin first, and then you do the missing value treatment so that your sample is not biased. So when I say your sample is not biased, we should have values for all the columns, right? So in empty cost dataset, it is nice, it is clean, it is better because it is a made up dataset. Like made up as in it is already available. But when you try something in real time, this is bound to happen, and this is how you the clean the data. So whenever you're trying to do a data science model, most of your time you will be ending up doing this data cleaning activity somehow or another, because otherwise your forecasts and predictions are going to be wrong. Is so that's the reason we are doing all the cleaning activities, so that we have a data set like empty cards wherein we have all the reasonable values in all the columns, so that we forecast or predict. Okay, so I hope this is clear for everyone. Do you guys have any question? Okay, so I'll move on to the next part. Okay, so where were we? Yeah, so the missing value treatment we have completed. So I'll just quickly check the time. Yeah, we have more than 1 hour. So yeah, it's fair. So the missing value treatment is something that we have completed. So now what we are trying to do is we are trying to uh, factor in the, okay, we are trying to convert the variables to categorical variables. Remember at the start of this session, I have told that the survived is your what categorical variable. So though there is numbers in here, it is treated as a categorical variable, like zeros and ones, and so that we are converting them from numerical variables to categorical variables. So how do you convert? So you can connect with the previous session that we had 2 weeks ago. So say factor of this one, then we'll see that factor with two levels. You see this, right? So once you convert them to factors, it automatically understands that, okay, so this is a categorical variable. 1 and 0 are treated not as numbers, but as categories 1 and 2. So you see here, 0 and 1 are strings. So in an easier way, we can understand that the zeros and ones are treated as different categories, not as numbers. Like you cannot do mean or median or mode on this factor, because now it has been converted to a factor, not a number, right? So similarly, the passenger class, right? So the passenger class is first class, second class, and the third class. So remember again, we said it at the beginning of the session, saying that passenger class is another categorical variable. It's not like number. Like you cannot, find the mean for the passenger class. It's just a categorical variable, right? So that's the reason we have, did this one, right? The survived. We have converted the variables that are present to the categories. So if we say if we see the same for passenger class, it's again the ordinal factor. Like it is named factor because we have given the levels as 3, 2, and 1. So that is the level that we are going to be. 3 being lower, 2 being middle, and 1 being the first class passengers. Okay. So I hope this is clear and simple. So now we'll go to the correlation plot. Okay. Huh. This graph, what it does is, it is the G-Galley is where this is the library associated with GC core. So what it does is it just gives the correlation between the variables. Okay. So if you see the passenger ID, there is literally no correlation with anything, right? So this is how you read the graph. With the passenger ID and fare, we do not have any correlation. Similarly, for age and fare, we have a weak correlation. So this is how these are the legends that you read with. So between the age and fare, there is no correlation. Meaning, so what is the difference? What's the difference it's going to take? So even rich people have kids, and poor people have kids. Like there is literally no correlation. But when you go to siblings and spouse and parents and children, so let's assume, I don't know, say the Titanic, the female lead, right? So whoever it is, Rose in that for that particular name, right? So the Jack and Rose. So for we can say it out. So that guy Jack, he doesn't have any family, he doesn't have any siblings, he doesn't have anyone, right? But the female lead, Rose or Kate Winslet, she had the entire family. So she had their mom and dad. So basically, we have a correlation in there because for her, the parents are there. So she'll be considered children for her parents, and her parents will consider for her parents, uh, since her both mom and dad were there, they'll be considered as siblings, I mean spouses, and the villain guy, he'll be some relative of the entire family tree. So we have a strong correlation, right? So mostly what it says is siblings and spouse, parents and children,